Hello everyone. This talk is part of the 22nd International Conference Computational and Mathematical Methods in Science and Engineering. The title of the presented work is Inverse Degree Index, Exponential Extension and Applications. The presentation will be divided into 5 sections. First, the topological indices and the inverse degree index will be briefly introduced. Secondly, some of the inequalities obtained for the ID index will be discussed. Thirdly, we will talk about exponential extensions of the topological indices and present some of the inequalities obtained for them. Then, the results of a quantitative structure property relationship analysis will be presented. Finally, the conclusions of this research will be discussed. Let's start with the introduction. In chemistry, it is often necessary to know the properties of substances formed by molecules. A natural way to visualize and analyze a molecule is through its chemical graph. This graph is obtained by taking each atom as a vertex and each covalent bond between two atoms as an edge between the corresponding vertices. Thus, for example, the valence of an atom can be seen as the degree of its corresponding vertex. One way to obtain information from the original molecule is to apply to the obtained chemical graph some function that is invariant under graph isomorphisms. If the image of this function is a subset of the real numbers, it is called a molecular descriptor. In addition, if a molecular descriptor correlates well with some physicochemical property, it is called a topological index. For more information on topological indexes, see references. Among the best-known and widely studied molecular descriptors is the class of vertex degree-based topological indices. These have been studied for more than 45 years, beginning with the work of Randic and the index that is named after him. During many years, scientists were trying to improve the predictive power of the Randic index. This led to the introduction of a large number of new topological descriptors resembling the original Randic index. Two of the main successors of the Randic index are the first and second Zagreb indices, denoted by M1 and M2 respectively, defined by these sums. Where G is a graph with a set of vertices V, and edges E, du, denotes the degree of vertex U, and UV is the edge that joins vertices U and V. This notation will be used throughout the entire presentation. The inverse degree index idea of a graph G is defined by this sum over all vertices of G, or this other sum over all edges of G. The inverse degree index first attracted attention through numerous conjectures generated by the computer program Graffiti in 1987. Since then, its relationship with other graph invariants, such as diameter, edge connectivity, matching number, and other topological indices, has been studied by several authors. See references. The concept of the variable molecular descriptors was proposed as a new way of characterizing heteroatoms in molecules and, in general, to try to increase the predictive power of already known indices. The idea behind the variable molecular descriptors is that the variables are determined during the regression, so that the standard error of estimate for a studied property is as small as possible. First and second general Zagreb indices are introduced as these sums. Note that these indices thus define generalize other important indices such as the aforementioned first and second usual Zagreb indices, the inverse degree index, the Randic index, etc. Let's start with the section, Inequalities involving the inverse degree index. The somber index of G was defined in 16 as this sum. Many papers have continued the study of the somber index. It has been shown that this index have good predictive potential. Our next result relates the somber and the inverse degree indices. Theorem 1. If G is a graph with maximum degree uppercase delta and minimum degree lowercase delta, then we have this relationship. And the equality in each bound is attained if and only if G is regular. The proof of this theorem is obtained by optimizing the following function. This can be done relatively easily because the function is decreasing in both variables. Then, we obtain bounds for this function. Substitute du and dv, sum for all edges of G, and the desired result is obtained. In 2015, Sheethall and Cannaber introduced the arithmetic geometric index as, and it has been studied by many authors. The next result relates the arithmetic geometric and the inverse degree indices. If G is a graph with maximum degree uppercase delta and minimum degree lowercase delta, then we have this relationship. And the equality in each bound is attained if and only if G is regular. The proof of this theorem is very similar to the previous one, considering a convenient function. The atom bond connectivity index is a useful topological index employed in studying the stability of alkanes and the strain energy of cyclocanes. The atom bond connectivity index of a graph G is defined as, and its generalization is defined as. Our next result relates the generalized atom bond connectivity and the inverse degree indices. Let's G be a graph with maximum degree uppercase delta, minimum degree lowercase delta, and an alpha less than or equal to -1. First, if lowercase delta is greater than 1, then we have this relationship. Second, if lowercase delta equals to 1, then we have this relationship. The proof of this theorem uses the same technique seen above. Except that, in this case, it is a little more tricky to optimize the function due to its shape and the alpha parameter. For this it was necessary to consider the symmetry of f, as well as to differentiate the cases for lowercase delta greater than 1 and lowercase delta equal to 1. Let's start with the section Inequalities involving exponential extension. The study of the exponential vertex degree-based topological indices was initiated by Rada in 2019 and has been successfully studied in numerous papers. We will consider two types of exponential indices. For a function of a single variable, a, the following general indexes are defined. In addition, for a function of two variables, b, that is symmetrical, these general indices are defined. The following result gives us an inequality relating two different exponential indices. Let G be a graph with n vertices and a1 and a2 topological indices if there exists a constant c greater than or equal to 1 such that c times a1 less than or equal to a2 for each vertex of G, then the following relationship is true. In the case that c is greater than 1, the equality in the bound is attained if, and only if, there exists a constant k, such that a2 equals c times a1 equals c times k for every vertex of G. In the case that c is equal to 1, then the equality in the bound is attained if, and only if, a2 equals a1 for every vertex of G. For the proof of this result, we use the convexity of the function x to the power of c, thus Jensen's inequality gives this first inequality. The second inequality is given because the exponential is an increasing function. From this, we obtain the desired result. The following result establishes an inequality relating a topological index to its exponential extension. Let us consider a symmetric function of two variables whose image is a subset of the closed interval from 0 to 1. Then these two inequalities are true. Moreover, if 0 does not belong to the image of b, then the upper bound is attained if, and only if, b evaluated in the degrees of the extreme vertices of any edge of G is equal to 1. For the proof of this result, we use the convexity of the exponential function and obtain the following inequalities for x between 0 and 1. Then we substitute the function be evaluated at the extreme vertices of an edge of G in this expression. We sum for each edge of G, and thus obtain the desired result. With arguments similar to these we can prove the following result. This is similar to the previous one for the case of the function of one variable. Let's start now with the applications section. In this case we have a quantitative structure property relationship study of the inverse degree index and the exponential inverse degree index. To develop linear models of some physicochemical properties of octane isomers, we select these properties for the study. Acentric factor, heat capacity at constant pressure, standard enthalpy of formation, standard enthalpy of vaporization, enthalpy of vaporization, and entropy. We tested this linear regression model, where P is the physicochemical property. Therefore, these linear QSPR models were obtained. In these figures, we plot the ID index versus the physicochemical properties of the octane isomers. The red line represents the linear regression model obtained. In this table, we resume the regression parameters and statistics of the previous linear QSPR models. Here, R, M, C, SE, F, and SF are the correlation coefficient, slope, intercept, standard error, f-test, and statistical significance, respectively. Note that for the properties, acentric factor, standard enthalpy of vaporization, and entropy, the ID index has good predictive power, with correlation coefficient values higher or very close to 0.9. Continuing, the same study was carried out for the exponential extension of the ID index, considering the same properties. And these linear models were obtained. Here we can see again the experimental values of the properties and the values obtained with the models in each case. In this table we can observe again the regression parameters and statistics for the QSPR models, obtained using the exponential extension of the ID index. Note that the correlation coefficient, standard error and statistical significance are very similar to those obtained for the ID index. Moreover, for the properties where both indices have good predictive power, the ID index presents slightly better values. In conclusion, in this work we studied the ID index, its generalizations, and its exponential extension. Optimal inequalities were obtained taking into account some graph invariants such as the number of vertices, number of edges, minimum degree, maximum degree, and other topological indices. In addition, a QSPR study was performed. From this, it can be concluded that both the ID index and its exponential extension have good predictive power for some physicochemical properties of octane isomers. In fact, the ID index is slightly better at predicting these properties. These are the references. Thank you very much for your attention. I hope you found the presentation interesting.